Hello students, this is Samson Deepak again from the Temple of Excellence. In my session 4 class today, in concern to the chapter Electric Charges and Fields, we will try to understand conceptual topics like electric field lines, properties of electric field lines, very frequently asked in the exam. We will try to understand what is an electric dipole and some of the concepts related to it. My dear students, if I review my session 3, I had discussed electric field, electric intensity, concepts of source charge, test charge and respected. Now, with whatever we have studied in our session 3, we use it as a tool to understand our session 4. Basically now, I start understanding what is meant by electric field lines. Basically, the physical meaning of something called as electric field lines. Point number 1, know that students, these electric field lines can either be curved lines or straight lines. There is no compulsion that electric field line has to be a straight line. There is no issue that it has to be only a curve. We say an electric field line can either be a curve or a straight line. Why do I use these lines? What are the significance of drawing electric field lines? Now, I told we have a unit positive charge. There was some space or region surrounding the unit positive charge, what we call as the electric field. And what should the electric field do? It should exert some electric force on that charge. What is the consequence of that force? Whenever you have a body and a force acts on the body, it is set into motion. Similarly, now the charge starts to move within the electric field. Why is it moving? The electric field is exerting some force on it, because of which it starts to move. Now, I draw certain lines which will trace the path of the UPC inside the electric field. What did the lines do? It will give us the path traced by the UPC inside the electric field. And these lines is what we call as electric field lines. So, what are electric field lines doing? They will give us the path traced by a UPC, the direction in which the UPC moves inside the electric field. So, my basic definition of an electric field line is they are either curves or straight lines. What are they doing? They will trace the path in which UPC moves, direction in which UPC moves inside the electric field. But my question, students, is there are hundreds of charges around us. Can we see them with naked eyes? No. Then how do I take a ruler and draw these electric field lines? Not possible. Therefore, we say electric field lines are imaginary lines. Please to understand, electric field lines don't have physical existence. They are imaginary lines drawn to understand the path of an UPC, and they are also called as Faraday's lines of force or electric lines of force. So, point number 1 here, an electric field line can either be a curve or a straight line. What do they indicate? They indicate the path traced or the path traveled by an UPC inside the field. Do they have physical existence? No. They are simply imaginary lines. We also call them as Faraday's lines of force or electric lines of force. Now, very important properties of electric field lines, always asked for 2 marks or 3 marks in the exam to mention the properties of electric field lines. So now to recall, I told a field line indicates the path in which UPC moves inside an electric field. Now the first property says, suppose I have a pair of charges plus Q and minus Q. What is the direction of the electric field line? In my previous session you have understood, if there is positive point charge, electric field acts radially outwards. If I have negative point charge, the electric field acts radially inwards. Now if I have a positive and a negative charge, what is the direction of electric field line? Please to understand, any electric field line starts from a positive charge and ends on a negative charge. What should be the direction? The field line should always start from the positive charge and it should end or terminate on the negative charge. Starts from the positive, ends from the negative charge. Most of the times you answer wrong in the examination. What do people write? Electric field line starts from positive terminal and ends on negative terminal. No, it is not terminal, it is charge. So the very first property of electric field line says that any field line starts from positive charge and terminates on negative charge. What if I have only a positive charge plus Q? The field line starts from the charge, goes away from the charge and ends at infinity. Very clearly you see these lines starting from plus Q and ending at infinity. What if it is minus Q? The field lines starts from infinity and ends towards the charge. So please to remember here, if I have a plus Q and minus Q, electric field line should start from positive charge and end on negative charge. If it is only plus Q, it should start from the charge, end up to infinity. If it is minus Q, it has to charge from infinity and end up towards the charge. The second one, very important. My dear students, I told an electric field line, the so-called line of force, can either be a curve or a straight line. So I consider a field line in the form of a curve. I consider a point P on this field line, some point P on the electric line of force, and I draw a tangent passing through this point. What did I do? I considered an electric line of force. Somewhere on that line of force, I considered a point P, and passing to that point, I have drawn a tangent. What does the tangent indicate? Please to listen carefully. This tangent indicates the direction of the electric field. What does it indicate? The direction of the electric field, where it indicates the direction of the electric field at this point P. So wherever you draw tangents passing through a point on the field line, the tangent always gives you the direction of the electric field at that point. Suppose one more point I consider here Q. Draw a tangent passing through the point Q. What is this tangent giving me? Electric field at this point Q. So wherever on a field line, if you draw a tangent passing through a point, the tangent always indicates the direction of the electric field at that point. So what do I conclude here? The basic conclusion is, at every point there is only one direction to the electric field. Please do remember this. At every point on the electric field line, there is only one direction to the electric field. At every point, electric field direction is unique. You cannot have two directions for electric field at a single point. Every point there has to be only one direction for the electric field. So tangent drawn at any point on the field line gives you what? The direction of the electric field at that point. Now, the third property is interesting. Do electric field lines cross or intersect each other? The answer is no. Two field lines never intersect each other. Why? What is the reason? Now, if suppose two field lines are intersecting each other, this is the first line, this is the second line, they intersect at the point O. Then at this single point, I can draw two directions for the electric field. When intersection happens, crossing of field lines happens. At the point of intersection, we get two directions for the electric field, which is not possible. Electrostatics says at every point there has to be only one direction. Therefore, very clearly we say electric field lines never intersect each other. Why don't they intersect? If they do so, at the point of intersection, there will be two directions for the field, which is not allowed according to electrostatics. Next, electric field lines do not form closed loops, contradictory to magnetic field lines. Remember, magnetic field lines form closed loops. Electric lines of force will never form closed loops. Why? If they form closed loops, again every possibility of intersection. If there is intersection again, at the common point, two directions for electric field, which is not allowed. Therefore, my dear friends, my dear students, please do note, electric lines of force do not form closed loops. They do not intersect, as well they do not form closed loops. Electric field lines do not pass through a conductor. Very important. Electric field lines do not pass through a conductor. Why? See, if you have a conductor here, this is the nature of field lines. Very clearly you see the electric field lines are not getting through the conductor. They are not passing through the conductor. What is the reason? Very first class, any conductor, inside the conductor there cannot be presence of any charge. We told, charges reside only on the outer surface of the conductor. Inside the conductor, Q is 0. When there is no charge, there cannot be electric field. E is 0. Therefore, electric field lines cannot pass through the conductor. So please do remember, electric field lines cannot pass through a conductor. Why can't this happen? The interior of any conductor is free from the presence of charges. No charges inside the conductor. When there are no charges inside the conductor, no electric field. Therefore, electric field lines do not pass. And finally, we say electric field lines are crowded in the region of strong electric field. If we indicate field lines crowded to each other, jam-packed, very close to each other, it means the electric field there is very strong. If they are separated, far away from each other, that means the region there is a weak electric field. So if you bring them close together, closely packed, jam-packed, that means it is strong electric field. If they are far away from each other, it means it is weak electric field. So these are the properties. What did we learn? We told field line should start from a positive charge and end on a negative charge. We told the tangent at any point gives the direction of electric field at that point. So, at every point, there is only one direction to the electric field. Two field lines never intersect each other. Why? At the point of intersection, there may be two directions to the field, not possible. They don't form closed loops. Field lines do not pass through a conductor as there are no charges and no electric field inside the conductor. If you indicate field lines close to each other, closely packed, it is a strong electric field. Far away from each other, it is a weak electric field. Now, moving on to the next session or next topic of discussion, we study something called as electric dipole. Very important in the study of crystals and solids. Electric dipole. Dear students, the word di means two and the word pole means charges. Understand? Di means two, pole means charges. So I understand somewhere a concept linked to two charges. We say an electric dipole consists of a pair of equal and opposite charges. ಎರಡು ಚಾರ್ಜ್ಗಳು ಅಂತ ಹೇಳಿದ್ದೀನಿ. So it should comprise a pair of equal and opposite charges separated by a small distance. Very key term, small distance. So what is an electric dipole? An electric dipole should consist of two equal and opposite charges which has to be separated by a small distance. So I consider here one charge is plus q, the other charge is minus q. They are separated by a small distance 2L. Why 2L? When I do the derivation, I will tell you all. Just now remember, the distance of separation is 2L. What is the significance of equal and opposite charges? See, one of the charge has magnitude Q. The other charge also has magnitude Q. Both the charges have the same magnitude, therefore they are equal charges. And why opposite? The polarity of one charge is plus and the other charge is minus. They are opposite in nature. So I have two charges which have the same magnitude and they are opposite in nature. So electric dipole should consist two charges which have the same magnitude and they have opposite nature. And what is the significance of saying small distance? See, now we told the space or region around them is electric field. What should the electric field do again? It should exert some force on the dipole now on both the charges. If the distance of separation increases, one of the charge may go out of the influence of this electric field. Remember, as I increase the distance between the two charges, as the separation increases, every possibility that one of the charge may lose the impact of the field, may go out of the influence of the field. Therefore, we say that the two charges have to be separated by a small distance where both the charges have to feel the influence of this electric field. Therefore, we say an electric dipole is a pair of equal and opposite charges, two charges of same magnitude and opposite in nature, which is separated by a small distance. Now, the distance of separation between the two charges. What I call as 2L is what we are calling as the dipole length. Length of the dipole. Yen length of the dipole andre? It is the distance of separation between plus q and minus q. ಆ ಎರಡು ಚಾರ್ಜ್ಗಳ ಮಧ್ಯೆ ಎಷ್ಟು ಸೆಪರೇಷನ್ ಇದೆ ಅದನ್ನ ಡೈಪೋಲ್ ಲೆಂತ್ ಅಂತ ಕರಿತೀವಿ. And the straight line joining the center of the two charges, axis anta heltivala, you call that as dipole axis. What is dipole axis? Straight line which joins the center of the two charges. What is dipole length? Distance of separation between the two charges, and this is what we call electric dipole. So ಹಾಗಾದ್ರೆ ಏನು electric dipole ಅಂದ್ರೆ ಎರಡು ಚಾರ್ಜ್ಗಳು ಇರಬೇಕು. One has to be plus q, the other has to be minus q. Both of them should have the same magnitude but opposite nature. What do you call the distance between them? Dipole length. What do you call the straight line joining them? Dipole axis. And these are the few examples for an electric dipole. Molecules of H2O, NH3, CO2, etc. What may be the total charge due to a dipole? 0. One is plus q, the other one is minus q. The total charge due to a dipole is always 0. So can I say the electric field also becomes 0? Charge illa. Net charge 0 adre electric field 0 agbekalva? No. Although the individual charges, they are separated by some distance. You may have plus q, you may have minus q, they may be separated by a small distance, but still they have some field around it which will add to the existing field. Therefore, even though the total charge is 0, total field cannot be 0. Why? They are individual charges separated by some distance. Now, as the last topic for this session, we discuss something called electric dipole moment. Electric dipole ಅಂದ್ರೆ ಏನು ಅಂತ ಗೊತ್ತಾಯ್ತು. ಎರಡು ಚಾರ್ಜ್ ಇರುತ್ತೆ, ಎರಡೂ ಈಕ್ವಲ್ ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಇರುತ್ತೆ, but one will be plus, the other one will be minus, and they will be separated by a small distance. Then what is electric dipole moment? What is the meaning of the word moment? The word moment refers to rotation. First PUC you have studied, moment refers to something called rotation. So if you observe, there was plus q, there was an axis, minus q, there was a field. What is the significance when there is an axis? Rotation. Which means because of this electric field, the charges start to rotate inside the field. They acquire moment. Momentum alla. Moment means rotation. From where do they get rotation? Because their centers are joined by a straight line, axis. And this is what is called dipole moment. Rotation of the electric dipole within the electric field. Impact, electric influence. ಏನು ಮಾಡ್ತಿದೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್? ಆ ಡೈಪೋಲ್ ಅನ್ನ ರೊಟೇಟ್ ಮಾಡ್ತಿದೆ. ಆ ರೊಟೇಷನ್ನೇ ನಾವು ಎಲೆಕ್ಟ್ರಿಕ್ ಡೈಪೋಲ್ ಮೊಮೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. It is indicated by vector P. Mathematically, it is defined as a product. Mathematically, very important, please to understand, Dipole moment is a product. Product of what? Magnitude of any one of the charge. ಎರಡು ಚಾರ್ಜ್ ಇರುತ್ತೆ, equal magnitude ಇರುತ್ತೆ. So we consider the magnitude of any one of the charge and the distance of separation between the two charges. Dipole length. So magnitude of any one of the charge into dipole length is what we call as electric dipole moment. My dear friends, please do keep in mind, electric dipole moment is defined as a product. Product of what? Q into 2L. What is Q? It is the magnitude of any one of the charge. What is 2L? Distance of separation, dipole length. That is what we call as electric dipole moment. P is Q into 2L. In vector form, vector P is Q into 2L. I need a unit vector here. I call as I cap, where I cap is the unit vector in the direction of the field. Usually for 1 mark, again they ask you the unit. Please to remember, it is dipole moment, charge into some distance. SI unit for charge is coulomb, distance is meter. So coulomb meter becomes the unit for electric dipole moment. And what is the direction? Again important. Please to know, vector P dipole moment is always from negative charge to positive charge. Field line ಎಲ್ಲಿಂದ ಎಲ್ಲಿಗೆ ಹೋಗೋದು? ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಇಂದ ಶುರುವಾಗಿ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಟರ್ಮಿನೇಟ್ ಆಗಿರೋದು. Dipole moment, it starts from the negative charge and ends on the positive charge. So how did we basically define dipole moment? It is the product of magnitude of any one of the charge into dipole length, Q into 2L. So please to keep this in mind. In my further derivations, wherever you have Q into 2L, that will give me my dipole moment. Product of the magnitude of any one of the charge with the dipole length. Now, these are the concepts which topically I have discussed in this session. Very important, called field lines. They are imaginary, they are curves, they are straight lines. But what do they give? The path traced by UPC inside the field. You have studied the different properties of field lines. You studied what is a dipole, two equal and opposite charges separated by small distance. And we also studied what is dipole moment. Vector P is Q into 2L with I cap. Product of magnitude of any one of the charge with dipole length. Hope you revise all these concepts for my next class, where trivially I will be doing 2 derivations. Have a nice day. Thank you.